Hey there, this is Ian Perry, Project Supervisor here at CanDrone. And I'm here today to continue off from the last video where we compared the Green Valley H800 LiDAR scanner and that same company's X3 series LiDAR scanner. We're going to proceed with comparing these two scanners now that we've processed some data. We have some key differences between the H800 and the X3-H. And key among those differences is field of view and the point density that we'll get when we're using these sensors in a forested environment. So before we dive into looking at data sets from these two sensors, I just want to touch on a little bit of theory with respect to field of view and overlap and how they play into one another for your data quality and density. So in this illustration, I have a narrow field of view on the left, and this may be the X3-H. And on the right, we have a wider field of view that symbolizes the H800. And in our model, we have a lone tree. You can see with the narrow field of view with 50% overlap that at the outer edge of that field of view, 35 degrees off nadir, there are some diagonal point returns picking up tree branches and tree trunk here. You can see over here on the right with the H800 scenario, these point returns are coming in at a more oblique angle and therefore would have more tendency to pick up the mid-story features in this forest, such as the tree trunk partway up. But you can see in both scenarios, we actually have the same amount of overlap. And overlap is no less important where you have a greater field of view, because if you actually decrease overlap, now you don't have the opportunity for more oblique point returns, and you will miss some of these features in the mid-story like you have on this tree depicted in the model. So if anything, in a situation where you have forestry that you need to scan and get vegetation information, 50% overlap is pretty crucial. In some cases, you may want to go even more than 50% to ensure that you have more oblique points more often on the same object of interest like this tree. So with that in mind, let's take a look at some of the data and understand what this looks like with real point cloud data. So with our data set, we have three different files to compare, and I'm first going to compare the two H800 data sets. The difference between these two H800 data sets is flight height, flight speed, and overlap. So in this top data set, I'll turn that on, that's the green. This was 120 meter flight height, higher than 50% overlap, and about 9 or 10 meters per second flight speed. So this would represent a major time savings in comparison to the standard flying parameters of the X3-H. Next in my list is the H800 with standard overlap, about 50% overlap, flown slowly, about 5 meters per second, at about an 80 meter height above terrain. And we can look at this direct comparison. These are geo-referenced together, so they should not have any shift. And we look at a profile with about a 10 centimeter buffer. And we pull this handle across and we zoom in. And this gives us an understanding of what data set is tighter, which this generally referred to as higher precision. I'm looking at a crushed gravel pathway. And what I see is somewhat surprising. There's a bit of a peculiar pattern of the data in its arrangement with the lower, slower data set. You can see it's kind of rendered in chunks, these vertical dashes. This is the lower, slower data set. Whereas the higher, faster with higher overlap actually renders a surface on the ground that is a little bit smoother, a little bit more uniform. Now this sensor in the spec sheet calls for plus or minus 5 centimeter precision. So let's take a look here, get a sense of the spread of this data. And what I'm seeing in the best case scenario is maybe close to 2 centimeter precision there. Some cases a little more, about 5 centimeter precision there. This is a rough crushed gravel pathway. Here is a bit of hard surface in the parking lot. And so you can see there's a lot of good uniformity in this, about 3 centimeter precision there, 2 there. Compare that to the lower and slower data set from the H800, and this seems to be a little bit less precise, which is interesting. Usually quality increases as you slow the LiDAR sensor down and fly closer to ground level. But here I'm seeing the opposite has emerged, and all other flight parameters have been kept equal. So this is an interesting revelation. Okay, so what I'm going to do now is I'm going to look at the forced cover, because that's what we really want to understand here between these two H800 data sets. I'm going to widen out this buffer to about 1/2 meter. Remember, the green data set is coming in at higher quality in the flatter, more open areas. And as I toggle these two on, you can see they pick up different aspects of the tree. The much higher overlap in the high flight at 120 meters does seem to be getting more points, as there is more opportunity for pulses at a oblique angle. Another feature we want to look at here is any kind of low point or ditch, and places where there's very, very dense vegetation like blackberry here in the lower mainland. You can see that this looks to resemble blackberry because there's almost no penetration of points beneath the canopy of this blackberry bush. I can see that the two data sets picked up different points, but neither one seems to be better for getting the deepest penetration underneath the thickest vegetation. Here's a good example of where this green data set, the higher overlap data set, actually picked up more of this tree trunk than the less overlap data set at 80 meters. You see the green, it pretty much uniformly picks up a tree trunk there, whereas this other data set, it's a little bit less filled in, and that would be bad if you want to get more information of the tree trunk, especially at the breast height level, where diameter at breast height is a key measurement for forestry metrics to understand timber volume when you're doing your inventory in a forestry setting. So now let's look at some accuracy assessments. We have qualitatively looked at these two data sets, but now I want to understand how they came in with respect to a control network that we set up on site with a base rover pair. So you can see the XYZ coordinates that we inputted into our post-processing software, LiDAR 360. And you can see here the root mean square error coming in at about 2.8 centimeters. That is for the higher flying data set with more overlap. And for the lower data set with less overlap, we actually have a slightly smaller error. It's a little bit inconsistent with the qualitative results that we were looking at. These quantitative results are showing us that the lower, slower data set is more accurate with respect to a control network of 7 points that we gathered with our base rover pair. So now I'm going to leave the data sets from the H800 for a second and take a look at the X3-H. Now this is the sensor by Green Valley with a smaller field of view that has been around for a little bit longer. I'm going to toggle on my better looking H800 data set and just do an immediate comparison of the precision in a more qualitative sense. What I can see right away is that the H800 has a little bit less spread. The green data set has just slightly less spread than the yellow data set, which is what you'd expect to see with a little bit higher precision hardware. Take a look at that on a hard surface like the parking lot. And again, the green data set is a bit tighter than the yellow data set. And for the price point, that is what we've come to expect. But I do want to look at the difference between the H800 and the X3-H in the forest, as that is where the H800 is expected to really shine in the situation. So here you have a tree with the H800 data set pretty well filled in, and the X3-H we see just a little bit less detail there. We take a few more profiles and look at results elsewhere. So from what I can see here, the difference between the X3-H and the H800 in the forest is not amazing. It's quite similar, in fact. What I'm getting here is, at least from a qualitative assessment, a lot of the same features resolved in these tree features with the H800 and the X3-H. Taking a look at the ground penetration, you can move along here and actually see that in most cases, that H800 and X3-H are getting the same features at the very bottom of the forest floor. This is a good example of where the X3-H just was not quite there. It didn't penetrate this thick canopy of what I think is blackberry or something similar. You see the green points made it through, but not remarkably different from where I stand here. This is a good opportunity to look at the number of returns that the H800 produced. We have the H800 bringing us 7-point returns. These are not discrete returns, but unlimited waveform returns. So this data is expected to be much denser. You can see turning off the various returns. As we move down the list, there are fewer and fewer points coming in with each subsequent return. I expect the first and second to have the greatest number of points, and I believe that that is indeed the case. With our X3-H, we have the 3 returns from the X3-H. So to summarize the difference between the H800 and the X3-H by Green Valley International, we've looked at overlap and its relative importance in a forestry application. A greater field of view does not take away the importance of overlap. If anything, you want to increase overlap to get the most out of the increased field of view. You get more oblique pulses and more of the mid-story of your forest canopy captured in your final point cloud product. A comparison of the two H800 datasets indicated that flying higher could actually yield better results if you have a higher overlap than 50%. That's going to save quite a lot of time, where when you fly higher, you cover more ground. A comparison of the X3-H and H800 datasets more qualitatively shows that the precision is going to be higher with the H800. That is, the fuzz or the uniformity of those ground points in open spaces going to be tighter, more uniform with the H800. And a more quantitative analysis of these two sensors puts the accuracy of the H800 at about a centimeter higher than the X3-H. We're coming in about 2.5, 2.6 centimeter error, and about 3.8 centimeter error with the H800 and X3-H respectively. I should add that high field of view is not everything. Let's say, for instance, that you're not in a forestry setting. Let's say you're in a mining setting or in an urban setting where you don't have vegetation to penetrate. There really is no need to have a wider field of view with laser pulses shooting out at a hard angle. If anything, in a mining or urban application, you want your points to be closer to nadir, because those that fall directly beneath or nearly beneath the sensor are going to be more accurate than points that fall further off nadir out at 50 degrees or more. So it really comes down to the use case and the user and what you prefer to get out of your LiDAR sensor. Certainly flying higher, flying faster, and flying over forested areas is going to be a job for this H800. But if you are generally flying a mixture of forests and more open landscapes, I would say that for the price point, the X3-H actually does a very, very good job. And in forestry applications, as we've seen here in this data set, the results are comparable to this much more expensive and heavier LiDAR system. Despite how close these sensors seem to perform, I would advocate for the H800 in a forestry setting. You're going to be able to get more accurate point information with more coverage of the mid-story, given that wider field of view. For more information about products like these, please follow our social media channels and always reach out to us with questions. We'd be happy to help.